change lanes a little bit. So our next speaker is Djorgovski. He is professor of astronomy and the executive officer of the astronomy department at Caltech. He's also the director of the Center for Data-Driven Discovery at Caltech. He has a PhD in astronomy, not surprising, from the University of California, Berkeley in 1985, a master's from that same institution in 1981, and a bachelor's in astronomy and astrophysics from Belgrade in 1979. He's a fellow for the American Advancement Association for Advancement of Science and distinguished visiting professor from King, some prestigious university. And I will embarrass myself trying to pronounce. He was the PI for the digital Palomar Observatory Sky Survey in its second epoch, 1992 to 2002. A co-PI for the Palomar Quest and Open Sky Survey, and a team lead for the big picture, if you've seen it, at the observatory. I also come to understand he has pioneered some novel methods for transportation and parking at Pat Creek Observatory. There are probably very few
carnation to get
I understand that very few will understand that reference, but for those of you who do, you will get the joke. Anyway, Djorgovski is going to talk about the 48-inch telescope.
Thank you, Andy. Excuse me for not being a very clear speaker because I'm just recovering from some bronchitis. Now, my charge was to talk about the 48-inch telescope, but there's more than one telescope involved, so I changed my title to talk about surveying the sky. Now, the 200-inch, of course, carries a lot of scientific legacy of Palomar, but it's associated with distant universe, going deep and so on. But I would say that equally important, maybe even more important part of Palomar legacy comes from small surveying telescopes, such as the 48-inch. Now, I think it's fair to say that modern sky surveys, because they did that in the past, starting with Ptolemy, right, were really invented at Palomar. They invented first by Fritz. And the key development was this innovative camera design by German optician Bernhard Schmidt that allowed to image wide fields on the sky, much bigger than what telescopes like presented. I'll show you an example. Apparently, Bernhard Schmidt was quite a character. He lost an arm in World War I and was just polishing all the optics with one thing. And supposedly, he subsisted on a diet of cigars, coffee, and grain. So he decided he needs a sky surveying instrument. He recognized that this is the exact thing that's needed. I'll come back to that. So really, there are two modes of doing astronomy these days. You can either go wide, but not very deep, which is what sky surveys are, or drill deep on some very special objects or very special pieces of the sky. And so big telescopes are not good at surveying the sky. Big telescopes are good at getting some precious data on things that somehow you decided are interesting. And you do this by discovering potentially interesting things with wide field surveys that cover a much bigger chunk of the sky. And here, let me illustrate this. The window on the right is a negative copy of one of the Palomar Sky Survey plates randomly selected in Andromeda. And the field of view from 48-inch is 6.5 degrees on the side. And I'll show you the full moon on the comparison. And the circle on the left will show you roughly what are the fields of view of big rectangular telescopes with 200-inch Keck or Hubble. And you can see that you really cannot survey on sky with Hubble Space Telescope. You can survey a small piece of green. So, back to Zwicky, our same protector. Zwicky built the first telescope at Palomar, the 18-inch. And I believe this was largely so he could find more supernovae. He and Bade were pioneering our studies and understanding of supernovae, including prediction of different stars. But supernovae are rare things, roughly one per galaxy per century. So you need to control a great deal of the galaxies in order to find enough supernovae to study. And so this is why Zwicky decided he needs a wide field sky surveying instrument, and there it is. So, of course, he did that in addition to many other important things, with discovery of dark matter and gravitational lensing predictions and whatnot. But as he was finding supernovae, he didn't find much. He also systematically cataloged galaxies and denser spots, clusters. I think most of them really, excuse me, pieces of large structure. There he is. The books that he's laying on are Zwicky's catalog of galaxies and clusters of galaxies. And that's actually been quite useful for some of the first pressure surveys of galaxies. So I would say Zwicky, along with perhaps Shapley, maybe the Leclerc, carries most credit for what you can call discovery of large-scale structure, recognizing how important and prevalent something like that is. Now, the telescope had a very useful subsequent life, and mainly in studying the solar system. Here, Gene and Carolyn Shoemaker and Eleanor Feline, who is also a competitor of theirs, and they were looking for Earth-crossing asteroids. Shoemaker was a geologist originally. He recognized that the big impact crater in Arizona was an impact of a small asteroid. It was Djorgovski. This was before people figured out that the impacts can kill dinosaurs. One of these large asteroid impacts can spoil your entire day. They also found a whole bunch of comets. The famous one that fell apart under Jupiter's gravity is Shoemaker D9, and all these pieces launched into Jupiter, showing what can happen to planet Earth as well. Nowadays, this is all done with more modern instruments and digital researches, but the telescope itself is over at the museum and you see it there. So, Zwicky's colleagues recognized that this was a really good idea, and this is why 48-inch Schmidt, bigger one, was commissioned at the same time as a 200-inch. It's basically a way to map the sky and find targets for the 200-inch to study. This is another one of those Russell Porter drawings showing what's inside, and the photographic plate is this thing in the middle right over here. And basically, this is the instrument that's did first, subsequent on the sky surface. So here is Hubble, and it was totally fake photos. The lights are on. I know. Should you always smoke a pipe when you have the Anyway, these surveys really had a huge impact on the astronomy. So the first one was in the span of 49 to 58, and main players behind it are basically all-star casts of astronomy. Then notice that there is no Zwicky's name there, and that's a whole other story. But the impact of this photographic sky survey, reproduced in newspaper copies, also glass copies, it was like as if for the first time you had a roadmap of the United States. It really was the roadmap of astronomy, not just optical, but radio and other for decades. And it produced science in of its own. Since you can't see all sky Palomar, its equivalents were done from Chile and Australia for the southern sky. And then in the intervening years, about half dozen other surveys were done for different purposes, possibly looking for fast-moving stars and such. And then this ended up with the second Palomar Observatory Sky Survey, 1995-2000, which was the last photographic sky survey. It was really the end of the photographic era of astronomy. Already it was clear that in order to do any science with something like that, you have to digitize those pictures. And all science is done on computer now. So the scans of this survey basically became what's called digital sky survey, DPOS, and used for a variety of things, possibly say Sky Star catalog for Hubble. Nowadays, these surveys are obsolete. I mean, they're historical, they're important, they made a huge impact. They stimulated more modern digital surveys. One of these famous survey, Fan Stars is a really excellent survey going on now. Hawaii, Gaia really released a phenomenal survey in space. Now, of course, there are all the other wavelengths, infrared. So it's kind of hard to show what one of these prints contains, but here's one little example. Minkowski student George Bell, for his thesis, looked over photographic plates looking for clusters of galaxies. He had a particular algorithm in mind, and the left side of the picture is approximately 2% of one of those Palomar sky survey images. You can see there's a little smudge there in the little box in the middle. Expanded box, take a picture with Hubble, and that's what you see at the right. So Bell's cluster catalog is the mainstay of extragalactic astronomy for clusters of galaxies, X-rays or otherwise. And I have to now honor a particular person, Jean Miller. Without her, none of this would happen. Thousands of photographic plates, which requires some real black magic chemistry to get them sensitized and dark and bend a little bit so they don't break and all that. And she was queen of the second Palomar sky survey and subsequently got promoted to be queen of the mountain. It was a much love for 200 inch and also happily retired. Well, thank you, Jean. So I mentioned one of the uses of these digital versions of second Palomar sky surveys, which was to provide Sky Star catalog for Hubble. Hubble telescope has a very tiny field of view. You want to point really precisely, and there was simply nothing available at the time of the launch that can serve the purpose of having sufficient numbers, sufficiently bright stars everywhere in the sky to use. And 48 inch essentially helped enable a great deal of Hubble science. That's not widely known, but it is. So let me illustrate a little bit how the way we do this changed. In the olden days, people would look with a magnifier on a photographic plate. But now we have digital scans, and this was from the D-class. And so you have a picture, you run a program, the computer finds sources, stars, galaxies, and so on, and a whole bunch of parameters for them. And then you do a little bit of data mining and somehow separate exciting stuff from just ordinary stuff. And then go take spectra and do some interesting science with it. And so the same algorithm basically has been done ever since. So even with DPOS, this large photographic or digital version of a large photographic survey, 48 inch was used as a survey instrument, 60 inch was used to support it to provide calibrations, 200 inch was used to get spectra, and that's where science is, and really exciting stuff. Okay. So this principle of synergy of telescopes, the right telescope for the right purpose, has been with us ever since then. Well, one last thing that I should say about the second Palomar sky survey, the digital version, is that before this first sample of what's now called time domain astronomy, it turns out these plates were taken with a substantial overlap. About 40% of the sky was being surveyed at least twice. And so you can look in the overlap regions, typically they're separated, this part is separated by some years, and look for highly variable things or things that are there and disappear. And so when we did that and then got spectra, it turned out that the most variable objects of the sky, not fancy, but objects always there, about half of them are some kind of star, variable stars, the other half are highly variable nuclei. The really interesting part came with finding things that only appeared once and never again, and back then, of course, it was too late, so we had no idea what they were. Now we do know. Mostly they're supernovae from dwarf galaxies, but also some of the cataclysmic variables of flare stars that we didn't see in the low state. So the first digital sky survey from 48 inch was done with the 3 CCD camera built at JPL called 3 shooter. But then this was followed up by this camera, built by physicists at Yale. And the Palomar Quest Sky Survey. Each of these four figures has a bunch of CCDs scanning the sky. And for a little brief period of time, this was the biggest CCD camera in astronomy. However, size aside, it was going to crash. This was probably the worst astronomical instrument ever made. I wasted 5 years of my life trying to fix it. So this is what it looked like. Actual telescope and the filters in front of all the CCDs. So that pretty much confirmed the initial impression. What are the most variable objects in the sky? A lot of them are cataclysmic variables for high amplitude flare stars. And also there is a great deal of active nuclei. So since you could catch these mysterious transients that appear and get spectrum while they're hot, so we already have then prototype pipeline called Palomar Quest Event Factory. We collect a great deal of data and do all manner of filtering. People have to look at the data and so on, and to find out what's real and what's not real. You get spectra of it, and those have to be supernovae. So the principle of this was good. The problem was that the data stream was so dirty that there were too many bad sources. And this is where Palomar transient factor comes in. But one piece of science that came out of Palomar Quest survey was discovery of dwarf planets by Mike Brown, who did not include the status of dwarf planet. Briefly, he was the most hated person in astronomy. Actually, Pluto Killer is his Twitter handle. He's proud of it. So essentially 48 inches led to the discovery of a new component of the solar system, this third group of planets brought into the gaseous and icy planets out there, Pluto included. And something Andy mentioned is we created a mural display for Great Observatory. People take a look. And it was, I think, probably still is the largest astronomical image ever. It's probably the best thing that came out of the whole Palomar Quest. Okay, so let's get more to more modern stuff. And Shri, who always has a good nose for what's a great new thing to do, seized upon this and did a very smart thing. He persuaded Wayne Rosen to buying a professionally built good CCD camera from CFHD telescope, bigger one then, and put that in 48 inch. And that was a vast improvement. It was just proper data. Okay. So this was the Palomar Transient Factory, which then segued to my immediate Palomar Transient Factory, and is now being succeeded by Zwicky facility. And Shri is a man of many talents. I think one of his main talents is being able to persuade people to do things for him. And I speak from personal experience. So he would organize, not just by camera, but this large team of people from many institutions to all pitch in, pull together, and that's really what it takes. So most of this science, I think, was on supernovae, various kinds, and I just showed you a couple of examples. Is one in M101. This was pretty exciting in the nearby galaxy. And PTF, IPTF discovered all manner of exciting cosmic explosions and new kinds of supernovae, some of which were predicted by theory and some which weren't. And it really changed the way we view that transient explosive sky, plus other things as well. And again, I should mention at this point the role of the 16-inch telescope, which is really being used to support these surveys for the past 20 years and thereabouts. First through photometric imaging, and then the spectroscopy, and normally we don't turn off the lights. But it's a very important part of the whole enterprise. And so now this is a slick new machinery with, again, 48-inch survey telescope producing the data. 200-inch used to get spectra of interesting ones, 60-inch used to also follow them up, and it all just keeps clicking. So this gets us to the last chapter in the saga, which is the Zwicky transient facility, remember that camera from CFHD, the camera, only covered a small fraction of the focal plane. Why waste the good focal plane with this fantastic imaging camera? And so, Palomar team and Shree's good leadership built this new camera that really paves the focal plane with CCDs. And it's tour de force in of itself for a variety of reasons. Named, of course, after our saint protector Zwicky, who really started so many different things. Sky surveys, supernova, etc., etc. And here it is being installed in the telescope, and it's there now. It compares extremely well with what came before. This is just compared to but compared to the other things. And essentially, you can do in an hour what previous generation of series of Palomar or CRTS have done for time to do. And the throughput is phenomenal, therefore you expect to see a lot of the sky. If you're systematically exploring sky for whatever purpose, this is what you want. You want to cover a great deal of observable parameter space as quickly as you can, and again, and again, and again. And as we call it, the panoramic cosmic cinematography. Here is just a field of view comparison of the ZTF with some of the famous regional sky surveys, and the sample of it is ZTF. It gets bigger than anything else. It stops in depth to a level that's possible to follow up with 200-inch telescope to get spectrum. So even though the LSSD is now being built in Chile, it will go much deeper. I predict that in fact ZTF would still rule the time domain even in the era of LSSD, because it covers dark sky, it also covers things faster, and it's geared for follow-up spectroscopy, which is for all of the sciences. And this, I believe, is the official first light image of ZTF. Orion, the force of Pendula. And I think, basically, you can see that the history of astronomy is still being made here at 48-inch. And I expect that, in fact, 48-inch may help with 200-inch in terms of significability in years to come. So with that, I'll stop at the end.
So are there any questions? Okay, well, let's thank George again. So we're going to have some light lunch refreshments now, and we'll be looking at touring various sites at the observatory just after that. As we make the transition to lunch, Steve advises me that we want to show something. While you get that set up, I'm going to frame the demonstration a little bit. So Palomar really is a community, and one of the incredibly important components of that community is our docent program. I'll amplify on some of these comments later in the afternoon, but we have a group of docents that have been working with us for about 14 years now. And they're really the public face of the observatory to the general public that come to visit, the kind of people that come up just because they're enthusiastic about learning about Palomar. And our docents are really there to represent the observatory. In addition to doing that, they also support various activities in the observatory, including part of the educational mission. So once a year, for instance, George's class, AY1, comes up to visit where introductory astronomy students get to meet and greet with a real live telescope. And the docents are there supporting them. And so I gather that this is an image that was taken as part of one of that support sessions.
Yes. And we as volunteers, we have a tremendously fun time with the Caltech astronomy students. And if you ever been at one of those nights, it really is fun, because part of it is visual observing with this old eyepiece that looked probably a Kellner eyepiece that came up with the tank. But then Paul Gardner from Caltech came up with the idea to expedite the viewing of multiple objects. Let's put a camera on it that goes direct to the screen. So it has to be a DSLR because no computer intervention is required. So we do a mix of those things. And just to tie together a bunch of themes we've talked about, M87, the P48, not a scientific camera at all, but the actual camera is right over here. This is an image of M87 we took. The camera is obviously horribly matched to a 60-inch telescope, but you can actually see the galaxy, and you can actually see the jet. And it's a lot of fun to see that, especially if we have very good seeing and we have nice planets.
So I didn't get a chance to introduce, that was Ken Searcy, one of our very experienced and very generous docents who worked with us. Okay, so I think I'll release you for lunch now. You can get a chance to get some of the questions we have in the back of the room. And we will get started on transportation to tours at about 12:40. So please, help yourself.